Hey, just an introduction to myself, Andrew Spiker. Pretty easy to find online if you're looking for follow-up questions that you don't get answered afterwards. I have been an individual contributor engineer on this project for the last year and became a product manager for it internally inside of Netflix, and more recently became the manager for the team. So deep in the project from the beginning. What are we going to learn from this session? First, we're going to start about why Netflix is using containers, some of the use cases and scale. How did we get there? What technologies did we end up building to use containers? And then finally, talk a little bit about the work we've been doing with ECS. So everybody knows of a little company called Netflix? Okay. Some interesting numbers. We're 86 million members strong. We went worldwide, except for a few countries. We are running out of 3 different regions of the world in terms of Amazon regions. We run on, our containers are smaller, but in our VM world, we're in 100,000 VM category at this point. Lots and lots of microservices. Probably the most interesting number up here is in North America, we do 1/3 of the internet download traffic every night. That's kind of fun. Containers. So why containers? Hopefully you all know that we're quite big in virtual machines. We built, which this is showing up here is a actual live screenshot of the microservices network with all the traffic coming in on the left and going all the way down to the data tiers on the right. We're very cloud native. We've been on the cloud for years. We have no data centers. Everything I'm going to show you here, I'm still on call for. Our team owns and operates. We're completely DevOps. And it's totally elastically scalable. And very highly resilient. You know, for folks that don't know, we do chaos testing against our own systems. So everything you show up here, I show up here, we've got a random process running around shooting instances, daily. So we did this all with VMs. You know, why did we need containers? Really, where it came from was developer velocity. So being able to innovate. If you look at Netflix and some of our key values for what we do in infrastructure, at the very top is being able to get features that make our experience as pleasing to you as possible, as fast as possible. Then comes resiliency. It should always be on. It should be no different than electricity. You should always be able to watch a movie. It finally comes down to efficiency. A lot of people come at containers from an efficiency play. That's not why we were coming about it. We had AMIs. We do baking. We do immutable infrastructure. But we didn't have the there we go. We didn't have the ability to do local iterative development in the same deployment artifact that we were doing in production. And this was important both for being able to round trip up, but also round trip down. So if something happens in production, being able to pull down the exact image, run it locally, and debug it. We also had this great system around baking of AMIs that was built around operating system concepts. So you would bake to a Debian package, and you know how to do upstart scripts and that kind of thing. But when people were trying to just run an application, they just wanted to write their application and its dependencies and simplify that build artifact. Finally was people, yes, they understand instances, but do they really want to understand instance types? They'd rather just express their resources and let someone else, i.e. myself, manage those resources for them. Talking about real value that we've realized over the last year of using containers, there's actually, I think it just came out on the tech blog, talking about some of the work that we're doing in our algorithms around encoding and how we were doing some stuff in load bandwidth markets that we were able to do faster than any other competitor. An example that came out of this is with using our container platform, setting up a really complex infrastructure for doing a wide-scale algorithm test was taking about a month. With containers, it's down to a week. We also have what we like to call a distributed, eventually consistent monorepo, i.e. we do not have a monorepo for our source code. We have all these microservices, and they have upstream consumers. And when we change things like our build infrastructure, we change things like our cloud platform libraries, or we change a microservice that 10 other people depend on, what happens? Typically, we run the tests on it. It passes the test, yay. The next day, the people that depend on it build their stuff. It doesn't pass their test, boo. And they have to go through this cycle of debugging it, all the consumers. What we did with this system, once we could run some massively parallel build systems, is now we can automatically build not only the tests that someone is running, but all the tests of everyone that depends on the component that we're changing. We call that system Niagara, and it's just literally saved hundreds of hours of debugging of upstream systems. And then the final one here is in the services space, we've been working in a container space with these smaller runtimes like Node.js, and people that were used to writing just Node.js scripts for our edge didn't really want to understand what infrastructure was. They wanted to say, hey, I just want to code the application. I don't want to have to understand how to package it, what instances, resources, all that kind of stuff. We could let them focus back on their application. So a question we get a lot is, why didn't we pick another container management solution? Why did we build our own? The fact is, most of the other container management solutions out there are focused on the data center or crossing data center and cloud and abstracting the cloud that was working under them, or even multi-cloud. For folks who don't know, we're all in on AWS. So we wanted an accelerated, highly tuned to Amazon container solution. We also had this amazing cloud platform that I talked about with microservices, and we just needed that puzzle piece that was a cluster manager for containers that would fit into that existing cloud platform. We didn't want to have a lot of the other solutions out there have continuous delivery aspects built into them. They have service discovery. They have telemetry systems. We didn't need all that. We just needed a container cluster manager, just like we had a VM cluster manager with ASGs. So, and finally, pretty important, also really not ready for the scale that we were at. So where did we come into containers? This is a little history as we build through. We started with batch. Batch users, as I was saying, kind of want to focus on their application. They've got some workload that needs to run. They've got a couple files that define their job, a couple dependencies and libraries that define how that job works. And they just say, can please someone just run it to completion reliably? They don't want to understand what an instance size is. They don't want to understand what auto-scaling groups are. They don't want to understand an operating system for that matter. They just have something that says, please run this for me. We had some definite experience with containers, not Docker containers, which we'll get into in a second. We've tech blogged about both of these, our workflow engine, Meson, our stream processing system, Mantis. We're using straight up C groups and Mesos for a very long time at Netflix. So we knew this technology could work for us. It was pretty simplistic isolation, but the most important part was they were very specific packaging formats. So if you wanted to run a Spark job, you code the Spark job, you deploy it as a Spark job, or you want to do a Mantis or Mesos job, you would do exactly those packaging formats. If you want to run something that doesn't fit into those frameworks, you're out of luck. So enter Titus. So Titus is my project. That's our logo on the left-hand side there. And what it is it's a container execution engine using Docker at the bottom with a lot of AWS integration, which we'll go through. We do the resource management and optimization on behalf of all the jobs that are coming into it. And at this point in time, it was just batch job management. Giving you an idea what batch is to us, we do algorithm model training. So it's kind of fuzzy because there's so many things on it, but this is a model training that's spanning out to all the languages, I think, that we support, and then filtering, merging, all these kind of things. Each one of these would turn into a Docker container that would get run in massively parallel scale in our infrastructure. We also, in this space, use GPUs. So we do deep learning, do neural nets. And we started with G2s. We use the NVIDIA Docker driver to map up the NVIDIA drivers so the programs could load it, as well as the devices up into the Docker containers. And now, this is like really cool. People get GPUs on demand. So they're like, OK, I just package up a Docker container that's going to CUDA. I'll go ahead and code that up. And I'll let somebody else run the infrastructure that makes those GPUs available to me. We started on G2s. We actually just recently moved to P2s, 8XLs. And we recognized about a 2x performance improvement of moving to the P2s. We haven't done the work yet to sort of optimize to the newer features that are available in the GPUs and P2s. But just moving from G2s to P2s, we got a 2x performance improvement. Talking about some of the other use cases, media encoding, I sort of already covered a little bit earlier. But you think about a video coming in raw format. It usually gets chunked up. Then each of those chunks have to get encoded in all kinds of different encoding algorithms in all different formats for your TV, for your phone, for your laptop. And that's just a lot of work that has to happen. It happens in batch. So we run that in this system. We also do watermarking, which is pretty cool. This is where some of our time-sensitive batch came from initially. So this is, for folks that don't know, I hope everyone knows, we have originals. So we have a lot of content that's original to us. That means we have a lot of content that has to go out to people before you guys see it. The most interesting one in the watermarking space is when the scripts go out to the actors, the PDFs get digitally watermarked to who we're sending it to. So you can imagine a big file comes in, it gets transcoded out many, many different times with different watermarks. In the case of a video, it's going to have the actors, and you're going to see green screen, like their name behind them. So if it gets out, we know who gave it out. And all this is happening as batch in our container. Another thing you'll see in batch is everybody wants to write reports, hourly, daily reports. Probably the most interesting use of the report is we have this big CDN that serves all the movie bits. All the reporting for our CDN network is built on top of the Titus container cloud and containers. So we learned some lessons from batch. First, Docker and having a more generic, here's my files, here's my entry point, gave us a more general batch processing system than we ever had before. We also found that scheduling and containers kind of go hand in hand. You can't just start doing containers, you need to schedule the resources. And given that we're on Amazon, we can do something that those other cluster managers don't do yet and elastically scale. So as workload comes into our system, we'll actually scale the underlying resource pool, get the jobs done, and scale it back down. And then finally, we'll talk more about this as we go towards the end. It was easy initially when people were like, well, I have a batch job, it has to be done sometime before tomorrow morning. But then people started to show up like the original engineering team and say, hey, I have these scripts, if they don't make it out by tomorrow morning, shooting doesn't happen. So time-sensitive batch starts to show up as well. Ignore these numbers, because we have to get our slides in really early for reInvent. This was the numbers on 11/7. I just pulled it up for last week. And this says test and prod. Don't think of test and prod. Actually, the whole the build system that I talked about, Niagara, runs in test. So to test and prod for us here are actually prod. Our customers are running in both. We did 600,000 containers last week in Titus. We peak at thousands of containers per minute, and we peak up at 3,000 virtual machines that are sliced up to handle these containers, mostly across R3s and M4s, which are both pretty beefy boxes. So batch is interesting, but what about services? So easy, right? We'll take Titus, we'll add now, instead of batch in the job management tier, we'll add service. We'll reuse all that great AWS integration, we'll use Docker. Services are just long-running batch, right? No, much more complex. So this is where we spent a lot of our work over the last 3 quarters. Services constantly resize. There's auto-scaling requirements. They have more state. A batch job is either running or it's not. A service job is, well, it started, now it's registered in discovery, now it's ready for handling traffic, and there's a lot more state management. And underlying both of those, as people that maintain the resources below them, it makes it really hard for us to upgrade our infrastructure, which we'll touch on more as we go. The other thing is that amazingly resilient DevOps, microservices, what other acronyms can I throw in there or buzzwords? There's a lot of tools at Netflix that made that work for services, for virtual machines. We had to make those same tools work for containers. So there was quite a bit of expectation for reusing the existing well-defined tool sets. But probably the hardest problem was networking. If you're going to run a bunch of containers on a single virtual machine, and you're thinking about virtual machines, and each of them have an IP stack. Maybe it's like the blue plugs up here. It's really easy. Once you go to containers and you start making a multi-tenant and everyone's sharing the red wire, it gets a lot harder. So we sat back and said, what are our requirements as we do networking? We wanted full IP stacks for every container that wanted an IP stack. We did not believe in port mapping. We did not believe in proxies, other things that could possibly make multi-tenancy work, but wouldn't work for applications like Akka and other things that hand out endpoints that have no idea if you've done some network virtualization around them. We wanted a full IP stack. A Also, I think Werner talked about this morning. We didn't want to leave security behind. So we wanted security group support. We wanted IAM roles. And then finally, you don't want one of your containers taking 90% of that red plug and everyone else fighting for the last 10%. We needed bandwidth isolation in our networking. So how did we get that done? We did two things. We wrote what we call our networking driver that's integrated with VPC, and we wrote a metadata proxy. And I'm going to take you through how we did each one of these. So our networking integration with Docker. So how do we get VPC to work with Docker? We have this thing called the executor that runs on each one of the host nodes that is told to start containers. When it's told to start a container, it creates a networking namespace. It does this by, it can reuse if it's already been, this has already occurred, but taking you through a new case, it will create and attach an ENI to the virtual machine. It'll adjust its security group, and it'll give it an IP address. We will then launch what we're calling a pod root container. For folks that are familiar with Kubernetes, it's really kind of a similar concept. So we start a pause container, which is nothing more than a long-running sleep that takes no resources. And we configure that from a Docker perspective with net equals none. It means don't set up any of the networking stuff. We're going to do that. We then will configure the virtual interfaces. We'll create some routing rules that associate it with the right ENI to get it back out to VPC. We'll configure a metadata proxy, NAT, which I'll talk more in length about. And then we configure via traffic control the bandwidth. All of this, what we're calling the pod root container. And basically, it's just a container to hold all the information about networking that we're going to use. So then at that point, oh, sorry, let me go back. At that point, we return back to our executor what that container ID is for the pod root. And we then will launch the real application container. So the one that the user wanted to run, we'll say create the application container, but create it with the networking namespace of the pod root. So it just associates itself with all that networking goodness that we just gave it. I talked about a metadata proxy. How many people familiar with the metadata proxy? OK. It's not everyone, so let me cover that real quick. So there's this magical URL that if you're inside a virtual machine, 169.254, 169.254, that things in the Amazon SDK will call to get IAM credentials, get what's your instance ID, what's your AMI ID. There's all this basically who am I information that's in the Amazon metadata service. And we didn't want all the containers seeing the hosts because we don't want the containers to get the IAM credentials of the host. It may have very different needs from a security perspective. And we also didn't want to confuse the containers to say, hey, what instance am I? Well, you're instance 123. The other container says, hey, what instance am I? Instance 123. You're not the same instance. So what we did was we wrote, as we configured the networking, we NAT in this server that we run on each of the hosts called the metadata proxy. If the container asks for 169.254, 169.254, it basically gets sent to local port 9999. And if it asks for what's my IP address, what's my instance ID, what's my host name, everything that the VPC networking driver figured out in the past, it's going to return that information instead of the host's information. If it asks about things that are very specific to virtual machines, it's going to go, I don't know. That doesn't really matter to you. So you're not going to get back what your AMI is of the host. And then most importantly, we wanted Amazon SDK-based applications just to continue to work unchanged. So when we schedule a container, we'll actually pass down what the IAM role is of that container. And when the container says, hey, what's my IAM role back through the metadata service, which is how it works, give me my credentials, we'll assume role into that role, get the credentials, and pass them back to the actual container and do that on their behalf. Anything else that's not blacklisted or whitelisted, we'll just proxy back to the original metadata proxy. Putting it all together, you can take a picture, but these will be in the slides. This is basically the mess of networking that you have to get working. So starting on the left side, you can see that would say maybe be a batch container. So it said, I don't need a routable IP address, but I do want access from a security group perspective. I want to be able to reach out. What you can see is because of that happening, we created an ENI1. We associated security group A with it. And we give it an IP address, but we won't let it accept traffic. We'll just let it get out. Containers 2 and 3, you can see are both asking for security group X. So what we were able to do is co-locate them on ENI 2, and you can see IP1 and IP2 on ENI 2, we give back to containers 2 and 3. Container 4, which is a very different set of security groups, so it's using Y and Z, we'll have to allocate yet another ENI, ENI 3 for that, and give it IP address 3. All of this is done and configured via Linux policy-based routing. Traffic control gets applied to do bandwidth isolation, so we can guarantee the same megabits, whatever container 1, 2, and 3 asks for from a megabits per second perspective, we control via traffic control and don't let anyone get more than what they ask for. And then finally, we'll NAT into all these containers of the metadata proxy. Additional AWS integration points. On behalf of the containers, we realize if they write log files that are in a rotated format, so it has like the timestamp or the .1, .2, when we see those occur, our executor is uploading those log files to S3 as they are being rotated. We also give people access to directly view any log file inside of the container. And when the container shuts down, we'll make sure all the log files get up. I don't think I touched on it here, but we also, through Docker exec and some trickery, we actually have on our bastions an SSH command that can let you get into the container, and it looks like you have a shell running inside of the container. We isolate disk from a quoting perspective. We use ZFS for that. So if you say, I want this many gigabytes of disk, everybody can make sure they get the amount of disk that they were requesting. We also do sort of the user data. So every container gets started with a set of environment variables. Also, we mount in a script file for people that don't want to use environment variables of what cluster are you in, what your application name is, all the things that you would expect to come down through user data. We also do instance type selection. So I said before, users don't care about instances, but we care because we want to run their applications most efficiently. So if we see an application is memory hungry, like an algorithm training job, we'll say, well, your CPU to memory ratio is X. That means we're going to land you on R3. We're going to pin your entire job to an R3. If you're more of a service-oriented job and your ratio is like a 1 to 2 or 1 to 4 ratio there, we'll put you on the C4s or M4s, and we'll pin you to that. We do that as part of the scheduling system as opposed to letting the user control that. I'll cover how we do the elastic scaling later. I also said we wanted this system to integrate with the Netflix infrastructure. What I mean by this, most of these things up here are open source. So Spinnaker, Atlas, the next one's Eureka, Edda, and then Simian Army at the bottom. We have all these technologies that people expect to use when they're doing CI/CD deployments to our cloud infrastructure. They use Spinnaker. When they're looking up information about what's giving insight into the application and how it's working, they go to Atlas. When they register and interconnect from an IP perspective, they go to our discovery systems. We had to make each one of these systems work with containers. When we started, most of these systems basically deduped based off the IDASH instance because they thought there would only ever be one thing that was reporting in from an instance. So you can imagine what happens with something like health check when I have 3 containers come in, all registering with the same IDASH instance, and now like 2 of them are healthy, 1 is not. Last one in was kind of winning, which was a big problem. So we did extensive amount of work in each one of these systems to bring multi-tenancy back into them where they could realize that a container ID was different than a virtual machine instance ID. We did that for 2 reasons. One, this is basically on the left-hand side in the blue is where we were before with virtual machines. So we're running service applications. They have certain cloud platform libraries that are in them that do metrics, IPC, other things. And they basically were running in clusters. They were running in clusters based on the AWS Autoscaler, which we all love and know and love. We wrote a job control system for services that looked like the AWS Autoscaler. So it has clusters that have stack, detail, sequence number, and application name, which is how we code into an ASG what an application versioned ASG is. It has min, max, desired, as you would expect. And if you adjust min, it starts things. If you adjust desired, it starts things. If you drop max, it stops things. So basically, we have service control that does all the same things. Now we can do both service and batch behind that same job control system. The two reasons why I did this is when people interact with this system, developers interact with this system, they deploy with Spinnaker. They go to telemetry system, Atlas. They go to our cache in EDA, and there's lots of systems that build on top of that cache. They go to our service discovery. We didn't want them to go to different systems when they were in containers than when they were in VMs. So we kept all those external interfaces exactly the same. The second thing is, for a very long time, at Netflix, we're not saying, hey, everyone that's in a virtual machine, you got to move to containers. That's not our thing. As I talk through some of these use cases, the cases where it made sense is where we're new cases is where it makes sense. We wanted to be able to operationally debug the systems the same. So I didn't want to have people that are working in an application that's in a virtual machine that's connecting to a microservice in a container have to know that, well, in the virtual machines, I'm going to use VPC for the networking, but in the container cloud, I'm going to use some overlay network or whatnot, and I have to debug them differently. We wanted to make sure we leverage all of those existing systems from an operational perspective as well. How many people have seen Spinnaker? Oh, awesome, awesome. So for people that haven't seen Spinnaker, this is our deployment pipelines, our CD system as a service. This is, as a developer at Netflix, this is how you work with a microservices network. What you're seeing here typically is you'd see these little green chiclets. The green chiclets actually represent, they'll be green if they're up and in discovery and healthy. There'll be various colors if they're not one of those things. And they usually represent a virtual machine. So you could go out and see some tiers that are pretty big, lots and lots of these chiclets. And then you can do various deployment pipelines against them. For people that are using containers, they go to the exact same thing. This is actually a personal project of mine at open source called OSS Tracker. And it's running in containers. The difference is you can see there's a little alien, well, not alien head, I guess robot head with Titus as the little icon there, as opposed to it would be the blocks if you were running in Amazon. When they create the server group, they say, which cloud provider do you want to use? And this is a little of a misnomer, right? It's on the left, if you pick Amazon Web Services, you get virtual machines. On the right, if you pick Titus, you'll get containers running on top of Amazon virtual machines. So it's not like we're moving clouds. We basically have a new IaaS layer on top of the existing IaaS layer from a Spinnaker perspective. But now the deployment artifact starts to change. So for folks that have seen Spinnaker for virtual machines and AMIs, typically there's a trigger that kicks off your pipeline that says, hey, there's a new build that's been built in Jenkins of an OS package that now is ready to be baked into an image. With containers, it differs, right? So now we have this deployment artifact that is the image, so I can kick off a deploy pipeline now based on a Docker registry. So in this case, what this does is it'll kick this pipeline off every time a new label, i.e. a new version of my Docker image shows up out in the Docker registries that we run. Creating new server group is mostly the same. The biggest difference is down here in the left-hand side, bottom left. Instead of saying, hey, I want an R3.8XL instance, I say, I want one CPU, I want this much memory, I want this much disk, I want this much network. You just express your resources. You don't think about instance types anymore. But then we wanted to make sure things continue to work. So you can see, because of our work that we did in the VPC driver and the work in the metadata proxy, you can still assign IAM roles and security groups to this cluster of containers that's going to get started. And most importantly, the deployment strategy is exactly the same. So we have many different deployment strategies, many different ways people approach deployments across Netflix. They can now use this because at the end of the day, Spinnaker treats the things it's deploying as instances and clusters, and now we have instances and clusters in containers just like we had them with virtual machines and auto-scaling groups. And from an operational perspective, all the same stuff is there. So at a glance, you can see what your instance is. I think in this case, I clicked on the first chiclet here. It tells me that the task ID, which is the container, is Titus 4036, and it's the first partition, third worker. It tells me what job it's running of. Think of that as ASG. It's going to give me both the host's IP address and the container's IP address. So very similar to what we had before, but now I just list resources. I don't have to list what instance size it's running on. But all of the same insight actions and operational actions still work, whether now that it's in containers. We've also done advanced integration like Chaos Monkey. Again, I think I covered this a little bit at the beginning, but now Chaos Monkey is integrated with Spinnaker. Chaos Monkey is a little process that runs around, and every part of my infrastructure, it shoots one of the instances at least a day. We enable that for containers, especially now that we have this abstraction layer of Spinnaker, that Chaos Monkey can just say now, if it's on Titus, I'm going to kill containers. If it's on Amazon, I'm going to kill virtual machines. So people even think about resiliency in the exact same way they think about in virtual machines. Telemetry was a little bit more work. So we actually leveraged Intel Snap open source technology. What you're seeing up here is this is the dashboard that anyone would go to, whether they're in virtual machines or whether they're in containers. And the difference here is now instead of NF node is like the instance ID, it would be, in a virtual machine, it would be I- something, something, something. In the container world, it's this nice, beautiful, long UUID. Definitely cattle, not pets. So those are three different instances, and I think, what did I put up there? Their CPU time. The other thing is you can see for system level telemetry, we're pulling that out of the C group metrics as opposed to pulling it back from the host operating system. All of our same tagging works. Everything works as before. This then allows people to do alerts and dashboards on top of this in a very transparent way, whether it's containers or virtual machines. Let's talk a little bit about scheduling. I said they go hand in hand. This is open source, something called Fenzo. Basically, the heart of our scheduling system is this open source library called Fenzo. It's not a scheduler. It's a library to help you build schedulers. And what we found was if you write a batch job management, you write service job management, write stream, maybe interactive, you end up writing a lot of the common boilerplate scheduling facilities that we decided to put in the library. So we abstract what we call task placement, which Fenzo does, from the job management, which is the life cycle of any one task. So essentially what Fenzo does is you give it a list of things that need to run. You also give it a list of resources that are available, and it makes a decision across those two and gives you a decision back of how you should place those resources. It does all kinds of scheduling objectives like bin packing, which is pretty important. We'll cover it for elastic scaling. It deals with totally heterogeneous sized resources, i.e. many different instance types, as well as containers. It also has callouts for autoscaling, which is another cool thing that I think is unique to us. So when you call Fenzo and you say, hey, here's all the work I need to do, here's all the resources I have to do, Fenzo can say, you know what? You don't have enough resources anymore. Why don't you scale up? And it'll tell us how much to scale up by or how much to scale down by and what instances to tear down. So pretty cool technology here. Also does all kinds of different constraints, which we'll talk about. And then really important as we get into the final part of the presentation, originally this was a library it was a library to help you write Mesos-based schedulers. And Mesos works by giving you a whole bunch of offers, maybe some that are duplicate out of the same machine. We rewrote it to also support ECS, where with ECS, I know how many resources are available on a machine right up front. So we call that single offer mode, and we've added that to Fenzo as well. So Fenzo, basically the high-level algorithm for Fenzo that you get to put plugins to, the things that are circled in orange, is it will, for every bit of work that you tell it needs to run, it'll go through every host set of resources it knows about. It will say, are there any hard constraints? Like if you need a GPU, you probably shouldn't run on an instance that doesn't have a GPU, so that's a hard constraint. You're going to evaluate the fitness. So maybe you want to fit based on memory and CPU and certain ratios. You can change that fitness calculation through plugins. Soft constraints is a great example, would be AZ balancing. So you say, I'd really like a third of these to land in AZ1, a third in AZ2, a third in AZ3. Now, maybe sometimes it can't be satisfied, but as long as the fitness is good enough, that's a soft constraint. And we basically evaluate that until the fit is good enough, and a certain number of hosts are evaluated, and then we'll return that result back to our scheduler with the task placement decisions. Talking about some of the cool things we're doing in scheduling. These are some pretty neat stuff. The amount of work that's in scheduling is just obscene once you actually start to getting into containers and some of the scale and complexity that we deal with. So first, when we started, we basically had a big resource pool that would auto-scale up and down, but everybody was equal. So basically, if you could imagine a scenario where you had a long-running service running, and then someone comes in with batch, and we do co-locate the work between service and batch. A big batch job comes in and takes the rest of all of the resources up to the ASG max. And it's going to run for the next 5 hours. And then all of a sudden, something happens in production, and we have to redeploy that service. Typically, when we redeploy services, we'll create a new version of the ASG before we tear down the old. No resources left. Well, let's just wait until that batch job finishes. Obviously, not a good solution. So we've just recently added into Fenzo and then our scheduler on top of it, multiple tiers of capacity guarantees. So we have the flex tier, which kind of operates the same way I just talked about, where you'd run things that really can deal with dynamic capacity and don't care about what their start latency is. And then we have a critical tier. The critical tier, people call Titus and say, much like reserved instances in the virtual machine world, they can reserve resources. They can say, I'm going to now be running on Titus this application, and it's going to use this many resources. We'll make sure Titus will actually run 2 resource pools, one for the flex tier and one for the critical tier. And in the critical tier, we'll make sure those resources are available with some buffering to allow people to do redeployments that guaranteed you're going to have guaranteed capacity, and your start latency is going to be no slower than starting a container, not starting up a virtual machine. Bin packing is really important to us, and really cool that we can do this because we're on Elastic Cloud. So it's very easy to do scaling up, very hard to do scaling down if you don't do bin packing. So what this shows is in that flex tier, we have min, max, and desired from an ASG perspective. And we'll continually adjust desired as there's more or less work in the system. But when we're scheduling tasks in Fenzo, we'll make sure that we land them. We'll do some level of AZ spreading for reliability, but then after that, we'll pack them into nodes as opposed to randomly spraying them across the nodes. So when that work finishes, we don't have a random task on each of the machines and we can't shut down any of the machines. We'll pack them in so once that work passes, we can decrease the desired back below and make forward progress in being able to reclaim those hosts. The next one would be constraints. I talked about this a little bit. The obvious constraint would, if I'm starting these 2 tasks, it would be nice to have a soft constraint or even a hard constraint if you choose to, that these, when jobs start, that they get sprayed across availability zones. But there's also some other really interesting sort of business impactful constraints that are interesting, right? So application locality. So if I put the edge server right beside the remote, basically the edge API right beside supporting services, I can get some interesting benefits in terms of latency. If I'm doing data streaming, I can consider data locality, that it would be nice if this part of the pipeline laid beside this part of the pipeline. And again, doing that in both a hard and soft constraint way for optimization, but then if that's not possible, being able to still run the workload. Another one that we've done recently, and this gets back to, I had a slide that said it's even harder to upgrade underlying hosts. We treat everything in Netflix as immutable, including our container infrastructure, which is quite challenging. So imagine I want to make a change to the Titus infrastructure. What that would mean is I start up a new ASG to run my containers in, and it's pretty easy for batch because this new ASG, any new batch jobs will land in the new ASG. As the batch completes and drains out of the old ASG, they just disappear. But what happens for services? Because they run forever, so they're never going to move from the old version to the new version. We started with a really sort of naive approach to that, which was, well, we'll just randomly shoot them, and of course they restart, so they move. If you do that very non-coordinated, you can cause capacity concerns that maybe you shoot them all and they don't come back up. Oops. So what we did was, again, leveraging the infrastructure we had around us, is for service, we will actually, as part of our job management in the service job manager, we'll make calls out to Spinnaker and say, hey, this task that's running as a container is about to be rebooted. What's your deployment strategy? And that deployment strategy may be, Spinnaker will reach out, create a new instance, wait for it to come up, wait for it to be ready for accepting traffic. Once it's all green, we'll kill the task, and it will let Spinnaker do the continuous deployment aspects of doing that service task migration from old to new, and then we can completely drain the old cluster and shut it down when the tasks are all moved and healthy. So service usage is a little smaller than our batch at this point. We're doing batch predominantly in first quarter. In second quarter of this year, we started working with some early adopters. We looked at internal services. In third quarter, we actually started, there's various parts of the interface, if you know the right parts, that are actually running a dual path mode right now, where you'll make a certain request that has to be idempotent, by the way, but it's a certain request from one of the devices doing one of the things in Netflix. It will make a call down the microservices network in the virtual machines. It'll make a parallel call down the container network in all containers. That lets us operate the container network like it's live. It allows us to compare and contrast the results that come back from the containers and the virtual machines. And we just throw away the result that comes back from the containers at this point in shadow. We basically call that shadowing. In fourth quarter, which is getting short for me right now, so I have to go home, we are moving services to production. The biggest, and this is probably one of our biggest scale-ups as well, the production usage of services that we're attacking this quarter is in our stream processing as a service offering inside of the company. So we're using Flink for that. And we're running that completely in containers, and that aspect of our data pipeline is going to be running in containers in production hopefully by Christmas. Right now, we have about 2,000 long-running containers that we're managing, so a little bit smaller scale than our batch. Still small, but still growing every day. So everything we've talked about thus far, we haven't talked about ECS. So somebody would ask me, what about ECS? We started collaboration with ECS because, as Neil talked about at the keynote this morning, we realized why this is really cool technology. We don't want to forever own and operate this aspect of our technology. There's definitely some operational overhead in maintaining the underlying cluster state that's built into this. We also have all of this EC2 integration that we've done in terms of ENI-based networking, in terms of the IAM role support, all these kind of things that we know we could contribute back into the open source ECS agent and would get us to the point where we could collaborate with all of you as opposed to doing this just by ourselves. So how does Titus work today? To give you an idea of what work we did as we were evaluating ECS, there's a much more complicated version of this online if you want to find it under my slide share. But basically at a high level, we make both outbound and inbound calls through Mesos for scheduling containers. So outbound calls, think about a user comes in and says, I want to launch these containers, or I want to terminate the specific container, or reconciliation where we're trying to figure out the state of what we know versus what are the state of the cluster knows. But we get inbound events. So if over on the right-hand side, one of those containers dies outside of our control, the executor notices it, tells the Mesos agent sends a message back through master. That master message gets back to our scheduler, and we say, hey, it died, we're going to restart it. So we get an inbound call for that. Same thing with containers, container instances in the EC2 world, or hosts. If a container instance comes up and now is ready to participate in the cluster, or an instance gets shut down, we need to know about that. That comes, again, up as an inbound event to our scheduler, and we can take action on it. We did the first Titus ECS implementation, so you can see if you flip between these. Basically, we changed the control plane out for ECS as opposed to Mesos. I will say right up front, as part of this evaluation, we haven't done the full EC2 integration. We're basically just trying to show the control plane aspects of running containers. So the whole like IP per container and security groups and all that kind of stuff, we're not talking about that in this implementation. But still, at the control plane level, what we did is we integrated ECS, and it was all outbound. So we would launch and terminate containers. If we wanted to find out what changed outside of our control, we had to pull the ECS control plane. So we'd say, hey, we think this container is still running. Can you tell us the state of this container? At our level of scale, that immediately hit us with rate limiting. So we have a real-time scheduler that's making decisions every couple 100 milliseconds. We are then calling at our level of scale for give me the state of all this existing infrastructure that's out there. It's not a really good thing to do against a rate-limited API. So we started talking to the ECS team and had done some really great collaboration with them. I think you heard some of that in the keynote this morning. Basically, what we said is, hey, we want a quote-unquote real-time, not real-time in terms of like something that will run a pacemaker or something like that. Real-time in terms of we want to know as absolutely soon as possible when things outside of our scheduler's control changes. We want it to be event-based. We didn't want to be polling-based. And we started this collaboration. We kicked off a face-to-face meeting. We've done monthly interacts on this, and we've just done engineering-to-engineering level discussions. And where we landed up, I think this got announced a week ago, but it was also in the keynote this morning, was CloudWatch enablement for ECS. So now I get a back channel. So now, again, I can do launches, and I can do terminations, and I can do reconciliation, all against ECS. But I get inbound events. So if one of the ECS agents connects, I'll get an event from CloudWatch that I can pipe through SQS, and now my scheduler is listening to SQS, and it says, hey, I just saw a container host pop up. Start scheduling on it. If a container dies, the event comes up through CloudWatch, I see it through SQS, and now my job schedulers can take action on that and restart the task. So this work that you saw with CloudWatch events has been quite a bit of work between our teams from a Netflix and ECS perspective. I'm really happy to see this showing up. And I'll show you some of the analysis we did on top of that. So starting with that, reconciliation. Anyone that's writing a scheduler has to deal with reconciliation. So there's two systems at play. There's the control plane that knows of everything it knows is running, and there's their scheduler that says these are all the things that are running that we know about. We in Titus do a flip-flopping every 5-minute analysis that says, hey, ECS, can you tell us everything you know is running? And then we compare it to what we're running. And if we see things that are in ECS that we don't think are running, we can tell them to die. And then the other 5-minute flip-flop will do, hey, we're running all this. Can you tell us the status of that in ECS? And if we find ECS doesn't know about something we think is running, we can restart it. This is pretty good from an API perspective. So you're able to, essentially, that turns into one call to get the ARNs for all the tasks in the ECS system. And then you can batch call to get status updates about tasks at a batch size of 100. So essentially, whatever the scale of the number of containers you're running, divide it by 100, add 1. That's how many API calls you have to make. And every 5 minutes, that's not a problem at all. Where we still do have a problem that we're working through is in the scheduling side. So I talked about earlier that we peak at some times, and this is abnormal, but it happens. 1,000 containers being restarted within a minute's time frame. In fact, it's 1,000 containers instantaneously because someone has pulled, I'm redeploying this whole tier, and it's anywhere between 600 and 1,000 containers at once. We were able to, working with the ECS team, get that to the point where with increased rate limits, we were able to get through that. But the problem here is you end up with however many tasks you're starting, you end up having to make 2x the number of calls. So if I start, actually, I should have given you the numbers. I start 1280, so I'm doing R3 8XLs, 32 cores, times 40 nodes, that's why 1280. The graph here shows with the raised rate limits, I was able to start 1280 within a minute's time frame. So it went from 0 to 1280 back to 0 in terms of started tasks per minute. But you end up making, for that, it was 1280 times 2 API calls within a really short amount of time. So continue area of scheduling collaboration here is the first one is to address that second problem. So we'd like to see that register task and start task became one API call, and it'd be nice to have them as batchable. So I could start 100 at a time. Then if I'm going to do a couple thousand, divide by 100, that's how many API calls you need to make. So we're working through that. The other thing is we currently are managing more resource types, actually even more resource types than Mesos offered to us, but more than ECS as well, in terms of we manage the size of the disk available yet, we manage the networking bandwidth, and the ENI and security groups, which is actually part of the reason why we're doing that beyond Mesos is it's actually a 2-level resource, the number of IPs remaining within an ENI that's associated with a security group. We've been able to do that with the agent today by passing them back as attributes, but then ECS actually doesn't even know about these resources. It would be nice certainly as we restart schedulers and need a resync state if this was known within the ECS control plane. A couple other smaller ones that we're working through is we have a few more states that we're used to. So with ECS, it has pending and started. With Titus Today, we have starting versus started. Starting is when the agent actually says, I saw your request to start a container. Started is after it did a Docker pull, it did a run, it created the pod root, all those different things that occur. And we can take action earlier with a starting versus started state if we know the message didn't actually make it to the host. Some other ones I think that are important is working on name tasks. So right now, essentially a task has an ARN, i.e. a container has an ARN. If we especially consider network partitions and we go ahead and we start something, but we never get back the ARN, we're never going to know how to kill it because we associate a task number with that independent of what ARN gets selected from the ECS control plane. And these are the things that we're continuing to work on with the ECS team. So it's a work in progress. We've basically, those things we talked about on the previous slide, get those out of the way. Then we would look at taking the Mesos resource management and replacing it with ECS with that feature set. And at that point, we could contribute the open source aspects. Now, blocks that was announced this morning changes a lot of that. Still working through that, so keep tuned on that. But a lot of that is really exciting to us because a lot of this work that we've done, we'd like to be able to contribute to Amazon as well as all of you and have us all working on that together. In the future, you saw some of this announced today with ECS, with the, I forget what they called it, the constraints and the task placement advances in ECS. Fenzo is a nice pluggable library. We'd like to see that same pluggability in the task placement engine, kind of move up the stack another level. And then finally, moving up the stack to the highest level would be our job managers for service and batch being able to reuse the ones that are in ECS with pluggability that lets us bring our Netflix business concepts into that job management. So future focus for our teams. We want to, right now we do auto-scaling of the underlying cluster, but we don't yet auto-scale the service jobs themselves. ECS does that through app scaling. We're working with the app scaling team to do that as well. We also ask the people that are doing services today to provision for peak of failure. If you go out and look, we actually shift traffic around the world when there's issues, and we call that traffic integration. We haven't yet done that for the services that are running in the container cloud. We also want to get to even more SLA management for our service and batch. So right now we have these 2 different tiers. It would be nice if we could take the flex tier and run it inside of the critical tier and do preemption to kick stuff out when we actually need that reserve capacity back. We also have a system internally that's based on virtual machines that is basically a spot market that people can use our trough capacity as you guys go to sleep to do all kinds of things like media encoding. We want to make the container platform a platform that offers that to anyone that runs a batch job within the container ecosystem. I talked about pods for how we do our networking. For folks that are aware of pods, we believe in them pretty strongly. We want to take that concept out to the developers. It's kind of a hidden feature. We want to get that back exposed for how people break up their monolithic containers. And of course, as you saw in the slides, our scale just keeps going up. So that's going to keep us busy as well as we move into the future. So with that, there's Titus again, and we'll ask for questions.